Hello. So this video will take forward the discussion of the LCR systems. So we saw the first order systems and various responses to it, and we saw the impedance can be represented as R plus JX, where R is the resistance and ZX is the reactance, R plus JX. So resistance and reactance together make the impedance, and the reciprocal of impedance is what we call the admittance. So the admittance is again G plus JB, where G is conductance and B is susceptance. So conductance, susceptance, resistance, and reactance, these are some terms that we must remember, and these represent the circuit systems comprising of LC and R. So moving on to the next topic, we have the second order systems. A second order system can be represented as two first order systems cascaded, that is coming one after the other. And let's say they have here, for an example, we give it an input u, the first one gives an output y, and final output being v. So if they have time constants tau1 and tau2 respectively, these will be the equations of the two systems, that is tau1 dy by dt plus y equals u, and similarly for the second one. On eliminating y, the common term from both these equations, we get something like tau1 tau2 d2v by dt square plus tau1 plus tau2 dv by dt plus v equals u. So this is basically a second order differential equation, and this is what a second order system means. Coming to the LCR systems and applying it, we have a time varying source Vs, LCR connected in series in the first case, connected in parallel in the second case. For the first case, we'll have the equation from KVL as Vs equals Vc plus Lc d2v by dt square Vc plus Rc d2Vc by dVc by dt. So this is the equation for the first case, as you can see here, and for the second case the equation is here, that is Lc d2v by dt square plus L by R dVc by dt. This should be Vc, Lc, this first term, and plus Vc equals Vs. So the only difference in these two equations is the first derivative coefficient, that is Rc and L by R. They are different in these two cases. So on comparing, we find that they are equal to the same equation we got for the general system. And on solving this, we should get an answer that is comprising of the natural response plus the steady state response, or what we call the forced response. So this is what the output will look like. But for a constant source, the solution will be of the form some constant plus a constant times exponential plus another constant times another exponential with a different time constant. This can be understood by applying a constant source to this system which we started with. If we give a constant input to the first order system, it will give a constant plus a time varying part, and again these two terms will be given as an input to the second first order system, and from that we should get something like this. So if the input is of the form vp exponential st, a different case, that is an exponential input, we should get a force response that we have been seeing so far, that is h of s times vp exponential st, the eigenfunction. And on putting it back into the differential equation, we get the transfer function of the second order system, that is 1 by s square lc plus lrs plus 1 in the series case, and similarly for the parallel case. But I think it should be rc times s over here in this equation, because we had rc in this differential equation. That's a correction here. And this was the forced response which we got. But what about the natural response? Let's see. For the natural response, we will put Vs equals 0. The source free circuit will give us the natural response, and the next step in solving is guessing a solution. So since exponential solution has worked for us so far, we'll start with it. That is guessing Vc equals a exponential pt. On putting this in the differential equation, we get a quadratic in p. Now the discriminant of this equation for the solution of the quadratic will govern the nature of roots. So on further simplification, we get this square root term. In this is we are solving the series and parallel case side by side. So on the left part, you will see the series equations, that is the A case, and the parallel on the B case on the right side. So for the first case, if we have L by R square C less than 1 by 4 in the series case, or R square C by L less than 1 by 4 in the parallel case, we'll get real distinct roots. So P1, P2 will be real and negative, a stable system. And due to linearity, the total complete solution for this case will be A1 exponential P1t plus A2 exponential P2t. The next case being the identical real roots where P1, P2 are equal, but this time the solution turns out to be slightly different, that is exponential Pt plus t times exponential Pt. This is because in this special case, the assumption that we started with, exponential solution, does not work for this second one. So we have to actually solve the entire differential equation for this particular case using these values. And on solving, we should get a solution that is of the form exponential minus pt times a1 t plus a2. Thus only one exponential term. And the final case being the imaginary roots case, where in the series case it will be L by R square C less greater than 1 by 4, or this in the parallel case. The roots are complex conjugates. Why is this so? Why complex? Okay, but why conjugates? That is because the quadratic we started with had real coefficients. So we have P1, P2 that will be some constant, let's say sigma plus or minus j omega. It can be seen here. Since the roots are now complex conjugates, we'll get this complete solution of the form A exponential sigma plus j omega times t plus A star, that is the complex conjugate. It should be sigma minus j omega whole times t, not only j omega t. So on adding these terms, we get a decaying sinusoid. Decaying because sigma is negative for real systems, and this is a sinusoid. So a decaying sinusoid is the solution for this. We'll take this discussion forward in the next video, where we'll see the natural and steady state forced response in some more detail. Okay, thank you.